Okay. I okay. So I don't have much time left. I kind of wanted to do a. Let's actually work on a little bit of instead of doing anything else. Let's work on a fun example. So how many of you ride bikes from home to campus? 1, 2. Okay. So let's imagine, like from home to campus, your bike path contains 2 sections. One section is a good road, one section is bad road. So basically, because you want to optimize your time and energy, right? So you want to ride at different speeds when you are riding on the good portion of the road and bad portion of the road. So what's the total time it takes? So let's imagine the 2 portions of the road, each is L1 and L2, so that's the length. And you ride, length, and you ride at V1 and V2. So what's the total time it takes to get from home to campus? L1 over V1 plus L2 over V2, right? So that's the total time. So also because the roads are quality is different, the amount of effort or the amount of energy you spend is different on different portion of the road. So let's imagine the energy you spend on the first portion of the road is equal to, let's say, E1 times L1 times V1 is proportional to how fast you ride. It's also proportional to E1 plus E2 times L2 times V2. So let's say this is the time and energy. Now consider a scenario. You have to get to campus to catch a class, and you want to spend as little energy biking as possible. What speed would you ride? How do you formulate that into optimization?
So your constraint is that T is however much time you have.
Yeah. So your constraint is, I write it down as such that your T has to be, let's just say, equal to your T. So your T required is equal to this formula here, right? So what do you want to minimize? You want to minimize the energy, right? Okay. V1 plus E2 L2 times V2. So that's my optimization problem. Perfect. Now imagine a different scenario. Okay. So imagine you want to go home for dinner and you have only a certain amount of energy left in your body. And you want to go home to have dinner as soon as you can. What is that optimization problem? The opposite, right? So imagine you have such that my E1 L1 V2 plus E2 L2 V2 is equal to the E remain, okay? And you want to minimize the amount of time.
Less than E remain.
Yeah, less or equal to E remain. But if you think of it, right? If you actually get a solution that is less, it means that you can probably further increase the velocity of either V1 or V2 and get home faster. Right? That means that could not be a solution to the problem.
In general, is there a different way to deal with equalities or inequalities in Lagrange multipliers?
So yes, so there is actually a way to. I didn't talk about it, but like if there is an inequality, then it puts a constraint on the value of the Lagrange multiplier. Depending on the sign of the inequality, the Lagrange multiplier is then constrained to be either only greater or equal to 0 or less or equal to 0. So lambda cannot be of arbitrary value. So right, so that's the difference. Okay, so you have these two minimization problems. The interesting thing is that, do you think these two problems have the same solution or different solutions?
Different.
Why different solutions? Because I'm minimizing different things, right? But again, if I can think of the T requirement varying over a range, and also this U remain vary over a range, I would get a two family of solutions. And these two family of the solutions would actually be the same. Why? Because the Lagrangian is the same. The Lagrangian is always the objective function plus a lambda times the constraint, right? Objective function plus lambda times the constraint.
But you multiply lambda by the different thing each time, so it shouldn't give you the same.
The lambdas are different. The lambda in this problem would be the reciprocal of the lambda in this problem. If you think of it in another way, the optimal of this solution is always the tangential point between these two contours, right? You have two contours, and both optimization problems are basically the tangential point of different contours with respect to each other. So they are actually the same family of solutions, right? So these are some very good, interesting things to think about when you are looking into constraint optimization problems. And this very question actually extends a lot more into, let's say, if you, instead of having two sections, you have a continuous varying section of the rows, and you want to write at a particular velocity profile. It actually turns out that velocity profile is a single variable family of solutions, and that family is the same no matter if you want to minimize energy or minimize time constraint to the other. Alright, so I will see you on Wednesday to continue talking about optimization, but with a different focus on actually computing the derivatives we need.